Hello everyone and welcome. One of my subscribers requested that I do a deep dive presentation on Cilium. So I'm going to do this in two parts. In part one, we're going to talk about what actually Cilium is. Then we'll discuss a new and exciting new technology called eBPF, which Cilium has fully embraced. And eBPF provides a way for developers to write applications that run inside kernel, and so that makes them very fast. So as far as the agenda is concerned, again, you're going to see what Cilium is and what Cilium kind of sets it apart from other CNI providers at the moment, again, leveraging the eBPF programming. Then we take a look at what are the issues with IP table are as the number of services increase, and how Cilium and eBPF will turbocharge the performance of load balancing in Kubernetes. Then we take a look at eBPF overview, and then we kind of deep dive into how Cilium leverages eBPF for load balancing. And then we walk through a comprehensive walkthrough on how do we set up Cilium and some of its components that we'll be talking about. Hope you can join me. So what is Cilium? Cilium is really another Kubernetes CNI provider. What it currently sets it apart from other CNI provider is that Cilium has fully embraced eBPF. We will talk about eBPF shortly, but it's a technology that allows developers to write applications that is compiled and run inside kernel. So that makes them incredibly fast. And Cilium has embraced that technology and brought it into its capabilities or features that are listed here. So let's go through those boxes or features one at a time. So networking is really a CNI provider. So at its core, Cilium provides CNI capabilities for Kubernetes. So to kind of remind you, the CNI providers provide pod networking for Kubernetes. It also provides observability or tracing. It has a utility that you can install as part of installation called Hubble, as in Hubble's telescope, that provides distributed networking and security, observability, or tracing. So this is incredibly useful if you are troubleshooting network-related bugs that you have in your Kubernetes infrastructure. It also provides network security, L3, L7, and DNS-based network policies. It also provides, or is under beta right now, service mesh. So again, provides things such as L7 traffic management and load balancing, TLS termination, and etc. So this is kind of like issue that I covered before, and you can take a look at it. I'll provide the link up here. But the difference between Istio and Cilium is, again, Cilium will be embracing eBPF programming, whereas Istio depends on actually injecting sidecars into pods when you create pods. That creates overhead, and this could be very significant. So Cilium will do away with sidecars when it actually uses eBPF. So as they call it, they use Linux as a sidecar. So you don't need any more sidecar injected into your pods. It actually uses Linux internally. So we'll talk about eBPF shortly. And first, we want to see what problems eBPF is going to solve for us. So let's take a look at performance issues that you might run into if you have thousands or even maybe even hundreds of services that are running in your Kubernetes installation. It's kind of a recap. Kubernetes by default uses kube-proxy to create services and manage them. And kube-proxy by default uses IP tables to manage load balancing And in this, as you can see here, we have a simple service called Hello World. And we have two pods that are behind this virtual IP or cluster IP. So how does the load balancing actually occur? So in order to understand that, we need to go inside the IP tables, go to command line, and issue a command like this. Basically, you're telling IP tables, we are interested in the NAT table or network address translation, because that's how that's the table responsible for managing the load balancing. And then we are looking for a chain or entry point called kube services. So this kube services, basically when you run it, it will show you all the Kubernetes services that have been created. So we'll see that these are the services that have been created by Kubernetes, and then this is our hello world. We can dig deeper into this, and then the kube services chain that we kind of ran the command for act as a load balancer and distributes the packets to kube-scp. So this is the next set of chains that it get involved in load balancing. So if we run another command and then we use this as the command line or as the argument, then we'll see that now the services that deposit are actually behind this service. So kube-scp chain represents a service endpoint. It simply does DNAT, replacing the service IP and port with the pod's endpoint and port. So in this chain, basically, the IP address of the cluster IP is actually translated into the actual pod's IP address and port number. And then for each one of those, if you want to investigate what happens next, we'll see that we can run, again, commands for that. So the point of it is that it is very complicated. There's a lot of rules involved, even for a simple service as the packets arrive here and a decision needs to be made where to guide this packet. There is a multitude of rules that needs to be run, and that makes the performance really bad when you have a lot of services. So we can kind of summarize the issues that we'll have with IP tables and kube-proxy. For each service added, multitude of IP table rules must be added also. IP tables are not indexed, so this is a big problem here. They're sequential. So when you're looking for instance, kube service, dash service, there's no index involved. It has to go through all these rules and until it hits the desired search item that you're looking for. It's kind of akin to having a database or a table that has no indexes. You have to do a full table scan in order to find what you're looking for. Not very efficient. The other problem is that incremental changes are not supported. So when you make a change to the rule, you have to actually copy the whole rules out, make the change, and save them back in. And also, it was really never designed to be an efficient load balancer in extremely demanding situations. And this is where eBPF will help. I'll provide an overview of eBPF next. So as mentioned earlier, eBPF is a technology that allows us to create custom sandbox programs that can run inside the operating system without actually making any changes to the operating system itself. So typically and historically, things such as networking and security are those kind of important programs are run inside the kernel. And this is great because these are very safe, and secure. However, the downside is if you need to add capabilities to this or make changes, then you have to recommend those changes, and it goes through the recommendation process and takes maybe years before it actually ends up inside the operating system. So eBPF is a great way for us to shortcut that process so we can create capabilities that we need and run them at runtime without making any changes again to the operating system. So once we do that, the operating system then guarantees safety and execution efficiency as if natively compiled with the aid of a JIT, or just-in-time compiler, and verification engine. So we go through the process of how applications are created or added to the operating system a little bit later, but this is just kind of an overview of what happens. And the way that actually it all happens is that the Linux kernel supports a set of hooks. So these are eBPF hooks that then we can write custom code and attach to them. And these applications are actually events. So these events are fired when something happens. Cilium has what is called data path that uses some of these hooks. And these are some of the hooks that it uses. It's not the complete list, but these are some of the most important ones. The first one is called XPath, or XTP, or Extended Data Path, and is a hook that runs or it triggers at the earliest possible in the network driver and triggers a run of eBPF program upon packet reception. So this basically, it attaches to a network interface, and as soon as the packet arrives, this is fired. So it can write events and do whatever that you need them to do. The second type of hooks that Cilium is used is called traffic control, or TCP, or TC, ingress and egress. And these, again, are attached like XTP to the network interface. However, the difference between them is they will run after the network stack has done initial processing of the packet. So this event happens first and then followed by this event. And this actually, when we look at Cilium and how networking works, I'll show you that this Cilium attaches this to the VET, the virtual Ethernet of the containers, and then listens, and then we can apply then the security and policy and load balancing, based on what's coming and going. So we can manage and control what's coming and leaves the pods. Socket operations. So the socket operations hook is attached to a specific C group and runs on TCP events. And the last part is socket, send, and receive. And these hooks are run on every send operations performed by a TCP socket. So this is a kind of a nice picture of how everything comes together. So first of all, the use cases, the most important one are the networking, security, observability, and tracing. So those are real use cases that eBPF is currently being used for. And then we have the user space and kernel. So if you're familiar with Linux, you know that application that you run, they typically run in the user space. Obviously, they always interact with the kernel. So whatever hardware that you want to access, networking or memory, all of that, then eventually calls into the kernel. But your Java application, your Python application, actually it runs in the user space. And then there are SDKs that it can actually create. You need to use some SDK to create eBPF applications, and the number of languages such as Go, C, Lang, and Rust can be used to create those. Again, this is beyond the scope of this course, but let's kind of mention that these SDKs are available for you to write your eBPF application. And also it mentions some of the project. Obviously, Cilium is one of them, and also Calico also supports eBPF, but I don't believe it's as extensive as Cilium yet, but they also are working in that space as well. And in the kernel, these are the eBPF, the kind of the hooks that the custom application that we run. And so there are two parts to it. We have the application, the user space application that then take advantage of these events that are fired here. Another aspect of eBPF programming is really the ability to share collected information and also to store state. And maps are really the way to do it. And maps, we can think of it as collections that you can store stuff in it, and then you can share those information among the application that run inside the kernel, other eBPF application, and also those will be available to user space programs through a system call. So this is kind of a view of what we are talking about. So we have this map. So we have various applications here, eBPF applications inside kernel that can write to various different maps as they gather information. And also they can share those information through system calls with other applications. For instance, in this scenario, we have like send and receive messages, those events, and then through a process, those applications outside can access the maps inside kernel. And then as we go through the Cilium and how networking works, I'll show you how, for instance, the information about what pods are behind a cluster IP service, how they are stored inside maps. And this is by no means the exhaustive list, but this is kind of some of the example, the type of things, maps that can be created. Things such as hash tables and arrays, LRU or least recently used, ring buffer, stack trace, LMP, and so on. So let's talk about the scenario where eBPF would be helpful to use. Let's say we have a VM here and it's got a network interface, a virtual network interface. That VM also hosts a pod, and there's a service that is running inside that pod. The pod has its own virtual internet interface card, and is also connected, attached to its counterpart on the host. So this is how communication between hosts goes through this VET virtual Ethernet, and then the packets travel then through that corridor or to that connection to the pod. So let's say our requirement is here is this. All the packets that arrive at the VM's network interface at 0 in our case, so all the packets that arrive here, we want to inspect those and see if they are destined for port 80. Then we want to forward those through this VET to the service that can be executed. So let's go ahead and see how we can achieve that. So the first thing that we need to do is actually create an eBPF application. So this is kind of a partial view of our code here. It really, you don't have to understand everything at this level. And I'll go through that, and then hopefully that makes sense. So this eBPF application has a section, basically, what is the hook? At what point we want to trigger this? And this is to_netdev. So basically, we are talking about it really attached to this Ethernet here. And we want to, and the logic says if TCP DP port is 80. So again, our requirement is if the port, destination port is 80. So this is that part, then redirect to this. Otherwise, drop the packet. So that's really all it takes to create this simple application. So once we create that, then we need to compile that. So CLang is the compiler that we need to use. Then we compile that, and then that can be loaded into the kernel through the loader, to the BPF loader. And then over here, there's a verifier. And this is very important because this ensures that the application that we write is not going to do any damage to the kernel. So they are very strict. So there are very a set of things that you need to follow in order for your application to be able to actually be loaded then inside kernel. So assuming that everything passes, then we can, it will JIT compile it. So we have the native code here, and then that native code also, we can also create map if we need to. We need to save state information. We can also create maps. So let's see what happens when the packet arrives at the server here. Again, so this is actually being now triggered here. And then it inspects the packet that has arrived, and we'll see if it's the port that is running or destined for, if it's 80, then it will forward it to the pod here, otherwise drop the packet. So this is a very simple, again, walkthrough of how eBPF programs conceptually are created and work. So hopefully we have some basic understanding of what eBPF is. Now let's see how Cilium take advantage of eBPF and specifically eBPF maps to create load balancing for our applications. Before that, let's review what happens today, like the default mode, how services are created. So in this mode, we use kube-proxy and IP tables to create service. So in this scenario, we have an application called Hello World, and we have 4 services, 4 pods that are installed on 2 nodes, node 1 and node 2. Now we want to create a service that the client can call, and the load balancer will forward that call to one of these 4 pods. So we can go to the command line and issue kubectl expose deployment hello world -- port 8080. So the service will be listening on port 8080, and it will forward that to port 8080. So the pods will be listening on port 8080, and the type is cluster IP. So once we execute that, then API server will create a service entry in the etcd, and then the endpoint control manager will wake up at some point and create endpoints for that service, and the endpoints here will be the IP addresses and the port numbers that our pods are listening on. And then the kube-proxy then wakes up at some point and creates a cluster IP and also programs the IP tables. And we looked at the IP tables rules a little bit earlier. So that's what happens inside here. It creates the rules for load balancing, and then it happens on all nodes. So this is the default way of creating services. kube-proxy has another node. It's called IPVS. So this is IPVS mode. In that mode, IP tables will not be used. It actually will be relying on IPVS, so create the rules in IPVS, which is basically a load balancer in Linux. And IPVS does not use sequential tables like IP tables. It actually creates hash tables, which are a lot faster. So this is the 2 modes, and I have a video that I go in much detail on the kube-proxy modes. You can watch it by clicking on this notification here. Now let's see what happens when we switch to Cilium. So when we do that, we can ask Cilium, don't use kube-proxies. We're going to do away with kube-proxy altogether. And the responsibility of creating services now falls on Cilium agent that are installed as part of installation. So once again we go through the process, when the service is created, the Cilium agent is notified instead of kube-proxy, and Cilium agent actually creates now the service IP. So this would be the cluster IP, the port number, and the service. So each service has an ID. And then also maps that to endpoints, which are our pods here. And each endpoint has an ID also. And these are the IP addresses for our pods here and the port number. So basically it creates that table, which is in fact is an eBPF map. So after doing that, it then persists those inside eBPF. So now this is how load balancing now occurs. It's relying on eBPF rather than either IPVS or IP table. So this is the fastest possible load balancing that you can have here. And each one of, and when the calls comes in, one of these connection, basically there's IP address and port number, so that each one of these is a connection. So one of these connections is by random selected, and the call will be forwarded to that particular IP. So once the service is created by Cilium, let's see what happens when an application tries to access it and what happens, how load balancing occurs. So here we have, again, a simple application. We have the Hello World UI on one node, and then we have two pods which host the Hello World service. So this Hello World UI calls into Hello World service. And let's say we also have created a cluster IP. So these two are behind this cluster IP. So let's see what happens when the UI calls into this cluster IP. So basically we issue a curl and the IP address of the service and the port number, which is 8080. And then after that happens, then an Ethernet frame is created, and within that Ethernet frame, then we have an IP packet. So I'm not showing the Ethernet packet for simplicity here. I'm just showing you the packet, IP packet. So it has a source, which is the IP address of this pod here that making a request. And the destination is the IP address of the cluster IP. And the port is 8080 because, again, the service is listing on port 8080. And then the payload, basically, which is a request. And then that goes through the Ethernet of the pod here, go through the VET, which is counterpart on the server. And it goes through a number of eBPF applications that are attached to this VET here. And let's go through each one of those and see what happens here. So in the service, basically it looks at the eBPF service map that we show you, that I just showed you in the previous slide, and looks up for this service to see what are the endpoints associated with that. So, and by random picks one of those. Let's say it picks this guy here and rewrites the destination address inside that IP packet. It also creates a connection and track or eBPF connection or contract, and it has two entries. One is the source would be the IP address of this pod, and the source port, again, when you call a service, HTTP or TCP, a socket is created here locally. So that is the IP address of this socket here, and the destination. The first one is the IP address of the cluster IP, because that's the original call that it was making was to this, and the destination port and the service size SVC. It also creates another entry here. Again, the IP address is the same. The destination though will be this one because that's did a DNAT here, and it keeps track of this because on the way back, when the response is coming back, we need to change the source from this guy to the cluster IP, because that's what is expecting, because it initiated the call to this cluster IP, and it expecting to hear from this, not this guy here. Otherwise, it will drop the response. So after that, then it goes to another eBPF application. This is connection. Basically, it says, do we already have an established connection? Yes or no? And that is used for enforcing policy. And then it goes through what is called the identity eBPF map. And for each service, for each pod that is created, it actually creates an ID. So this is based on the hash of the labels that pod has. And then looks for that IP address here and finds the ID corresponding to this. So the IDs are created by Cilium because the IP addresses could change. And these IDs are then used for enforcing policies. And then goes to the next eBPF map, which is basically saying is this ID, and that is, does this pod, is this pod allowed to connect to the back end on port 80? Is it allowed? Yes or no? If no, then the package is dropped and it won't go any further. Assuming that it is allowed, so it continues its journey, and then the request comes to this Ethernet adapter here for the server. And so just to keep in mind that by default, Cilium uses VXLAN for overlay network. We can override that if all the nodes are on the same network, then we can bypass VXLAN. So if it goes through VXLAN, then additional packets are created or headers are created for this, so that it can be moved from one location or from one server to the other. If you don't know how VXLAN works, again, I have another video that you can click up here that talks in detail how VXLAN works. So assume we are not going through VXLAN, we're just going through regular LAN, and then that kind of continues its journey. It arrives here on this interface and then goes through the wet here and then finally ends up here. So not that this IP or this pod receives a request, then it starts working on the response. So the response would be the results of this, the request that was made. So the source would be itself, and then the destination would be the IP address of this guy here. And then again, it goes back now in reverse, travels back now here. And then over here, when it gets to this interface here, then Cilium checks for the connection map. So as we saw earlier, a connection map was created here. Now it checks the connection and see that this IP needs to be changed. So it does the reverse. So now changes the source from this guy to this guy, because that is what the original caller was expecting, because that's the service is called, that's the IP address is expecting to hear from. And it goes through that, and then finally arrives at here, and then we get the result, which is hello world and some more information. So this is a quick view of how Cilium uses eBPF maps to manage load balancing. In the next section, we are going to actually install Cilium on a brand new Kubernetes cluster, and we go through the process of how we can do that. But before that, let's take a look at what we really installed as part of installing Cilium on a cluster. The first thing that it will install, we need to install, is the agent. So the Cilium agent runs on each node in the cluster and listens for events from orchestration systems such as Kubernetes to learn when containers or workloads are started and stopped. It also manages the eBPF programs, which the Linux kernel uses to control all network access in or out of these containers. We'll also include install Cilium client, and basically it's a command line that is installed along with the Cilium agent. It interacts with the REST API of Cilium agent running on the same node. The CLI allows inspecting the state and status of the local agent. It also provides tooling to directly access the eBPF maps to validate their state. We'll also include installed operator. The Cilium operator is responsible for managing duties in the cluster, which should logically be handled once for the entire cluster, rather than once for each node in the cluster. Obviously, it will also install CNI, so I think we are familiar with CNI by now. It provides pod networking. It also interacts with the container runtime manager to create new pods. So the Hubble server runs on each node and retrieves the eBPF-based visibility from Cilium. Relay is a standalone component which is aware of all running Hubble servers. Basically provides a glass window into what's happening inside all other nodes that Hubble server is running, and provides a single API to provide visibility into tracing and visibility information. There are also CLIs, which is a command line, and UI, so we'll be able to consume or view visibility information and traceability information through the CLI and UI. In this section, we're going to discuss how to install Cilium into our cluster. So if you are on a public cloud, such as Google, Amazon, or Microsoft, or if you're using Kind to install Kubernetes, or you're going to install it on Minikube, they have a convenient way of installing those. Basically, they augmented those processes and included Cilium installation as part of that. However, in situations where you want to install it manually and you're on-prem, such as in my case, then we need to install it in a different way. And that's what we're going to walk through the process of how we can do that. So we are in Visual Studio Code, and then on top of the page, I've defined my cluster member. Basically, I'll have a master and a node. So I have a cluster which will consist of a master node and another node. And then on line 13, I have described here, run this on all Linux nodes that you want to join to your Kubernetes cluster. Basically, these are the prerequisites that you need to have on all server, except Helm. And Helm only needed on the master. You can install it on other nodes if you want to. There's no harm in it, but it's a requirement that on your master, because you're going to need to install Cilium using Helm. On line 16, we want to make sure that we have upgraded our Linux environment, because on line 18, I have described the kernel version. It says the documentation at the time of this recording, they're recommending 5.3 or 5.8 for the optimum performance. But I think you can get away with 4.59. I am 4.9, I believe. However, just do the upgrade and update your Linux environment to make sure you have the latest version. In order to see what version you have on line 19, you can run this command, sudo host navectl. So this is just one way of finding out what version of kernel you have. There are other ways of doing that, but and over here, when you run that, so it tells you the kernel version, which in my case, at the time of recording this, was 5.4. And then you go through the process and then install things such as a container manager. In this case, I'm using container D, and then the following lines here to configure container D and run it and start the process. And then we need to get the GPG key for Kubernetes from Google. And then we need to update the repository to include the Kubernetes also. And then on line 40, we need to install all the command lines needed, such as kubeadm, kubelet, and kubectl. Following that, we need to do some networking configuration. So from line 43 all the way here, these are all related to networking. So we need to make sure that we configure those. So I've already done that to save time. And then finally on line 66, we need to then download all the images that are required by Kubernetes in order to function. So we need to download that as well. So once you install those on all your nodes, then you're ready to actually initialize the cluster. And so that is on line 71, sudo kdm init -- skip dash phases equal to add-on dash kube-proxy. So basically what you're saying is initiate this cluster. However, do not install kube-proxy because as we mentioned, Cilium will replace kube-proxy with something which is based on eBPF. So let's go and run that. And it should take maybe a couple of minutes to get everything installed and initiate the cluster. And that's complete. And then in the last line, this is basically a command that we need to run on all other nodes to join them to our cluster. So let's go scroll down here. And I provided a placeholder here. Once init command has completed successfully, run this on all your nodes. So let's go ahead and run that. And I've opened another terminal here. And now this is a node, the other node that will be part of my cluster. So I'm going to run this on that node in order to it to join the cluster. So let's go run that. I get my password here. And again, it should take maybe a minute or maybe less than that to get that done. Okay, that's done. So we need to now go back to master again. Let me clear that out. Okay, and then on line 81, we need to create a hidden folder called kube. Basically, that's where the certificate, we need to get the certificates that was installed, that were generated as part of the installation process and copy them here. So let's go ahead and do that. And then we need to copy the certificates that were generated through the process and copy them to our folder. Basically, it will allow us to communicate with kubeadm because we need those certificates to run things such as kubectl. And then on line 83, we set the appropriate security on those. Okay, and then we are now ready to actually now install Cilium. And then the first thing that we need to do is download the Cilium CLI. So this is the command line that we need to interact with Cilium. So on line 86 through 89, basically this is how we're going to get the CLI from this URL. Then we make sure that do the checksum, make sure that it's valid and it's not tampered with. And then we copy, we extract or unzip that and then copy it under this folder here. And then we remove the file that we just downloaded. We don't need it anymore. We just delete that. So basically, this is how we download that and then we copy the CLI under this folder. I've already done that to save time. And then we need to also now add Cilium to the Helm repository on line 92. Again, I've already done that. So finally, this is the step that I'll be going to install Cilium. So this is the command. We need to specify the namespace, which is kube system, and replacement, kube replacement and strict. So this line basically says, make sure that we're not going to use kube-proxy. So the mode is called strict. And then on what node we're going to install it, we're going to install it on master. So that is the IP address of my master node. And this is the port number that will be running on. And by default is 6443. So let's go ahead and run that. And then it says you've successfully installed Cilium. Okay, so one thing I ran into here, although it was successful, but I've noticed that it takes some time for nodes to Cilium to install whatever it needs to install on nodes. But I've noticed that even after waiting a few minutes, sometimes it says that the node is not ready. So let's go ahead and run 104. Let's see how our nodes are doing. And we'll see that both of them are saying is not ready. So I'm going to give it a few more minutes, and then we'll check that again. And then if it's not, if it's still not ready, and which I've run into that before, I think it's a bug maybe in this early maybe versions of this, we need to reboot the server. So I'm going to pause here, and then we'll check again in a few minutes to see if it's still the case or not. Okay, let's check that again. Wait a couple of minutes. Let's run that again. And we'll see that still is not ready. So what I'm going to do is I'm going to reboot both servers, and then we'll come back again and we'll continue. And then we'll double check to make sure that everything is running appropriately. So again, I don't know if it's a bug or something. I had to reboot the server. So we'll continue afterwards. Okay, just rebooted, and let's see, everything's okay now. Yeah, both are ready. Now let's take a look at the pods here, and we'll see everything is running. So this is the Cilium operator that we talk about. So these two are the Cilium agent running on each node. So how many nodes that you have, it will create an agent that will be running on those. Okay, let's, next we want to verify to make sure that kube-proxy is not running anymore. So let's, on line 107, so basically we get the, all the pods that have Cilium in them, so, or created by Cilium, so these two are created. So I'm going to grab, so on line 108, I want to get the IP address of one of these. Really doesn't matter which one. So this is basically a capture the IP address of the first one into the variable, so we can echo that on 109. And this is the name of the, so we are going to now on line 112 to verify that this kube-proxy is not being used. So let's go ahead and run that kubectl exec -it. So we're going to exec into the pod and into the Cilium pod that we just grabbed. And then let's look at the status, Cilium status, and grab and grabbing for kube-proxy replacement. So let's go ahead and run that. And we'll see that kube-proxy replacement strict, so which means that it no longer uses the kube-proxy, the old kube-proxy. So this is one verification that you can run. Okay, let me clear that. On line 115, Cilium status. So Cilium status, basically, it tells us what is the status of Cilium. You want to make sure that it is running correctly. So let's go ahead and run that. And we'll see that Cilium okay, operator okay. Hubble disabled, we haven't enabled Hubble yet. And cluster mesh, we are not using it yet for this demo. So everything seems to be okay as far as Cilium is concerned. Now let's take a look at what interfaces Cilium has created so far. So let's go ahead and run that on line 118, IP link show. And we'll see that apart from obviously H0 is the Ethernet for that VM. However, everything else starting with Cilium. So these are what, for instance, the operator, the agent, and so on. So these are when the pods are created. So these are the vet part, the vet counterpart. So if you recall, when a pod is created, the pod will have an Ethernet interface, and then it has a counterpart on the other side on the host. So these are the ones counterpart on the host. And also, so there's a health, so on, and there's VXLAN. So by default, Cilium uses VXLAN. So this is a interface created specifically for VXLAN. Okay, let's clear that. And optionally, once we do a deployment, we can then copy the content of the cube file in our folder. We can copy it to other nodes. So if you want to run kubectl from other nodes, then you should copy the certificates that is in that folder, and we can copy it to the other server. So I'm not going to do that for this one. Okay, now let's do this section. We're going to run some tests to make sure that our cluster actually running. We can actually create pods. So on line 126, I want to untaint master. So by default, master is tainted, meaning that when you schedule a pod, it won't be scheduled on master. It will be scheduled on other pod, on other nodes, except master. But since here we only have 2 nodes, I want to untaint master, so to enable us to deploy pods or schedule pods on it. So let's go around that, and we see that says master untainted. Okay. And on line 129, you're going to deploy a hello world application. So kubectl create deployment hello world -- image. So this is the image that it's going to get from Google. So let's go ahead and run that. And we see that hello world was created. On line 132, we want to scale that to 4 pods. So you have 2 pods on each server, on each node. So let's go ahead and scale that. There we will see that now it's scaled to 4. Now let's take a look at, let me clear here. On line 135, kubectl get pods minus -o. So you'll see that now we have 4 pods in the default namespace running, and we have 2 on node 2 and 2 on master. Okay, that's so far so good. Now let's create a service for the deployment we just created. So on line 137, kubectl expose deployment hello world -- port 8080. So this is a port that service will be listening on, and target port is 8080. So that is the port that the container is running on, and the type is node port. So a node port means that we'll be able to call the service from outside the cluster using one of the cluster IPs. So let's go ahead and run that. We'll see that exposed. Now let's verify that on line 138, kubectl get service hello world, and we'll see that hello world is created. The type is node port. The cluster IP is this, and we have 2 ports. One, this is 8080 from internal, and this one is node port 31921. That's when you call from outside the cluster. Now, we can also verify that from Cilium perspective. So kubeexec -IT -encubes system. So this is the IP address of the Cilium that we got early on. And then we run this command, Cilium service list. So Cilium has got a CLI that runs on nodes. It also has another CLI that runs actually on the Cilium nodes. I'm going to discuss that more detail in the next video, but for now, we want to see, by running this Cilium service list, it shows us what are the pods, or what is the load balancer situation, what are the services, and what how they're load balanced as in regards to the back-end pods. So let's go ahead and run that. Oops. And these are all the services that so far has been created. And for our service, this is port 8080. And so these are the 4 pods that are behind the load balancer. So this is actually, the information is coming from the eBPF now. So there's no IP tables, everything is coming from eBPF. And on line 143, so again, to drive home that you're not using IP tables anymore. So let's go ahead and check to see if there's anything in the IP table. So sudo IP tables -save, and then we grep it into kube-svc. So we recall I mentioned that during the presentation that kube-svc, so that is the kind of the root of all the services that Kubernetes create. So let's go ahead and run that. And let's put my password here. And we see there's nothing in it, it's empty because you're not using the IP tables anymore. Okay, so to test the service we just created, I'm going to get the cluster IP. So this is the trick that I use, basically kubectl get service hello world -o JSON path, and I'm looking for .spec.cluster IP. So that will give me the cluster IP of the service. And then we can echo that on line 4146, echo cluster IP. So this is the cluster IP that we saw earlier. And we can get the port number also. So kubectl get service hello world -o JSON path, and here we're looking for .spec ports 0.port. So let's go ahead and run that, and then we see the port 8080. We specify that when we create the service. Okay, now we can curl based on these two variables that we just defined. Let's go ahead and do a curl, and you see that we get response from the service. So that's the service that we get response that we get from the service. Similarly, we can get the node port kubectl get service hello world -o JSON path, and over here we look for .json .spec.port 0.node port. So that gives us the node port number, and then we can echo it out. That's the echo port. And then we can also then test curl HTTP. So this is the IP address of the master, and then this is the node port that we just got. So let's go ahead and run that, and we get the same result, which is hello world response from all servers. So everything looks good as far as Cilium and Kubernetes is concerned. So next, we're going to actually now install Hubble. So if you recall, Hubble is allow us to see a traceability, like we can trace to see what services is calling what and what's going on inside our cluster. I'll cover Hubble in detail in the next episode, but for now we just want to enable Hubble, and that is on line 162. kubectl, or sorry, Cilium Hubble enable. So let's go ahead and run that, and it just waits. It says waits for Cilium. Make sure it's ready. Okay, and it says that Hubble was successfully enabled. So we can verify that on line 166, Cilium status. Let's go ahead and run that. And we will see that now Hubble is enabled. So in order to actually be able to interact with Hubble, we need to install the CLI. Let me clear this. And so from line 169 to 137, just basically need to go through this and get the CLI installed. It's going to download that, verify, checksum is okay. Then we copy it under the user, local user, and then we remove what we downloaded. Okay, now we can run Cilium Hubble port. So we need to, in order to access the Hubble API, we need to create a port forward to Hubble service from our local machine. And that is on line 176, Cilium Hubble port -forward and then ampersand. So let's go ahead and run that, and we will see that the results here. So that's the port. And now if we do a Hubble status, so we run into that. I've run that, we saw multiple times, and then for some reason, again in this version of Cilium and Hubble. When you do that the first time, for some reason, it doesn't work. So there's a workaround explained here. We need to delete a certificate, search secrets, and then recreate them. So on line 183, kubectl delete secrets minus n kubectl Cilium-ca. So let's go. So that's the certificate for that. And then kubectl on line 184, kubectl get secret minus n kubesystem Hubble ca secret minus o, and the rest of it. So unfortunately, we have to go through this in order to make that work. So and again on 185, we need to disable Hubble, and then we need to re-able it. Okay, now Hubble is enabled again, as you can see here. Let's go ahead now and try to open the port. So recall that we disabled Hubble, we enabled that. But again, is another bug here. If I run on for line 190, Cilium Hubble port forward, we'll see that we get an error that the port is in use, even though we disabled that. And so if I do on line 195 Hubble status, it tells us that the connection refused. So if I go back here and run this, and we'll see that now open the port. So there is something going on. Again, maybe some bug here. So if I do now, Hubble status, we'll see that connection nodes 2 and 2. So everything working okay now. And we can run Hubble observe on 192. And these are some of the connections that it found and is showing us. So again, I'll go through the Hubble CLI and we do some testing in the next episode. For now, I just want to get everything set up. If you guys are following, just get your environment set up. And then next episode, we go through Hubble in detail. I don't want to make this too long. We can also enable Hubble UI. So there's a CLI, the command line that is also a GUI. So on line 195, Cilium Hubble enable --UI. Let's go ahead and run that. Okay, we'll see that now. Hubble UI was successfully installed. Now on line 197, Cilium Hubble UI. So let's go ahead and run that. And we'll see that now we can go to the local browser. So let's just copy that. And then we can actually take a look at some of the report here. So this is the UI, Hubble UI. And then we can select, for instance, right now we don't have anything running, so there's not a whole lot of report we can look. However, if we go to the kube system, we'll see that Hubble UI is running and is connecting to Hubble Relay. And these are the connection status, for instance. So again, we'll go through the UI. Next time, we'll deploy some pause, and then we go through policies and Hubble UI and CLI to get a better understanding of how these things work. So this is kind of an overview of what Cilium is and what the components are, and then we install the components, and now we are ready to actually start using that. And then we go through again next time. We go through the in detail into the policies and the reports and observability. Thank you for watching.